All right, cool. How is everybody doing?
Doing better now that I witnessed that video.
Excellent. Yeah, it's hard to have a bad day after that, I think. All right, so my plan was to go through quick discussion of the final exam, look at the list of topics and so on. But um, before we do that, if there's any specific questions that people want to go over, um, we should talk about those first. So this was the list from yesterday. So any questions either from that list or just anything in general from the course that you want to go over? All right. Let's see. I'm good with the list. Okay. Cool. I'm just starting my video upload from the morning. Are we going to expect it to have a deep understanding of the various sorting algorithms? What I want you to be able to do is maybe answer some conceptual questions about those sorts, like, order of complexity, comparison of one versus another, but also be able to use different sort algorithms to show me the steps of sorting an algorithm, sorting say a list of numbers, or maybe if I show you a set of steps, tell me which algorithm was being used. So like those sample practice problems that I posted on Canvas a while back. Here's a list of 10 numbers. Show me how this list would change as you go through an insertion sort or a quick sort or something like that. So you should understand these algorithms well enough to apply them, but I'm not going to ask you to code them, for example. Cool. All right. So this is our last class. So this is the end of CSE222. So I want to tell everybody that I think you've done a fantastic job this quarter. I know a lot of people finished 224 maybe feeling a little shaky about C and still trying to understand some of the foundational concepts there. And I think across the board people have just come really far in figuring out, scanning, doing input, basic logic, looping, things like that, and all the data structure-y stuff, so pointers and mallocs and dereferencing pointers with stars and arrows and things like that. And I think people have just come really far, and I think everybody's in really good shape as far as data structures, and is in really good shape for moving on to CSE 223. So kind of sad that the course is ending, but definitely looking forward to the next course, 223, because once we start 223, we've got a basic understanding of data structures. We can use those to do things. So a lot of what we're coding in 222 is, implementing a linked list or a tree or things like that. 223, we get to use those and build on top of them. And we switch to Java. And once we're in Java, right, we have a very natural framework to do a lot of this kind of modular development that we've been doing, kind of barehanded in C, where we can just say, give me a tree, give me a linked list, let's put these together. And so the kinds of assignments we'll be doing in 223 will be more, larger things that actually do something that might seem interesting to us. So we'll do some network development, we'll do some game development, we'll do some GUI development, and that's a lot of fun. I think 222 is the most difficult course in the sequence. I think 223 is possibly the most fun, because we have so much at our disposal at that point. So I think that'll be a good payoff for all the hard work you've done up to this point. So definitely looking forward to that, and I just want to say thank you to everybody for all of your energy and effort in this course. What games can be created in 223? So we've done tic-tac-toe games in the past. We've done a dots game where make boxes with dots. But these are graphical, right? So they're played with point and click with the mouse, and you get to see the board. So a step up from high-low or stick picking. Will there be anything with double pointers on the final? Possibly. I mean, a double pointer is really just an array of pointers. And so, one double pointer that we deal with a lot is when we write a main function. This second argument is always a double pointer. And a double pointer, we sometimes think of it as an array of pointers. So if you want an array of strings, that's really a double pointer. If you wanted an array of linked lists, right, we could have, a struct node star. That's what a sentinel node looks like. If we do this, that's really declaring an array of sentinel nodes. So I don't expect to ask you explicitly about this, but it's in there, right? It's certainly there with second argument to a main program. And if you have to do an array of pointers to structures, that's going to look like a star star or a double pointer. But I wouldn't get too worried about it. All right, so we started working through this list yesterday. So we talked a little about structures, and arrays of structures are just like arrays of anything else, integers and chars and so on. So linked lists, most of the linked lists we developed dealt with sentinel nodes. You don't need a sentinel node, but if you have a sentinel node, then you have this convenience that this is what an empty list looks like. And even with an empty list, there's still a struct node, right, that we can pass around to functions and so on and so forth. And when I add something to an empty list, this does not change. What changes is this thing that the sentinel points to. So it's a convenience to avoid having to do what we do with trees, where we say, root equals add parentheses, or root equals delete parentheses. We don't need to do that with a linked list if we have a sentinel. But it's really just kind of a bogus node that's always there. And then basic structure of a linked list, right? Nodes point to other nodes. And that's common to most of the structures that we've talked about, trees and such. And the main operation that we do in a linked list is following this chain of pointers. So whether you're searching or inserting or deleting or counting or whatever, the main thing we have to do in the deepest guts of our code is follow this set of pointers. So, set your node equal to sentinel, and then set it to variable next, and set it to that variable next, and set it to that variable next, and it'll move you down through your list. So if we're searching, we do that until we find our data or we hit the end of our list. If we're deleting, we do it until we find our data, and then we set the previous node to point to the following node. If we're inserting, we do it till we find our insertion spot, and then we adjust pointers to squeeze our new node in the middle of the list. But the real coding piece there is, following this set of pointers from one node to a next. Doubly linked list is just the idea that we have, these nodes that normally have pointers going forward, but we can introduce a second pointer for each node which points backwards. And that's convenient because when we're moving through a list, sometimes when we get to the point where we want to do something, we need to know the previous node. And so if we already have a pointer in each node pointing backwards, we can just use that pointer to find the previous. Otherwise, we do this business with, previous current, previous current, previous current, where we keep track of those two. You should be able to think about or answer questions related to order of complexity for lists and, for other things as well. So order of complexity is looking at how the time required to do an algorithm changes as the size of the problem changes. And this was our starting point when we first started talking about data structures 10 weeks ago. We started with the idea of an array. And if you have an array of numbers and they're totally random, then searching is an order n operation, because the only way you know if something's in there is to check everything until you either find it or you run out of numbers. But if we sort this, then this becomes a log n, because we can play high-low. If this is sorted, we can start in the middle and say our number is bigger than that. We've thrown away half the list. We only have to search half as many things. And with one more operation, is our number in the middle? No, it's smaller. We can throw away another half of the list. So each time we do this, our list cuts in half. So a sorted list we can search in log n. But then adding something into the middle of a list, if we want to put something between here and here, we need to move everything down, and that's an order n. And so linked lists were an attempt to basically take the order n of inserting or deleting in a sorted list and change it to order 1. So if you have pointers connecting nodes and you want to put something in the middle, all you got to do is change one pointer, change a second pointer. So then that becomes order 1. So that's just how order of complexity plays into why we started talking about linked lists. All right, so you should be pretty comfortable with this, right? So this, if you have a pointer to something, this says what's the thing pointed to. If you have any kind of variable, this says what's the address of that variable. And this ties into pass by value and pass by reference. So if you have some main program, and let's say I have an integer I and I set it equal to 10, and I call some function and I pass I to it, and then I print I, no matter what this function does, I is going to be equal to 10. Right? I is a local variable to this program main, this function main, and I pass it to my function, but I don't actually pass I. What I pass is the value. So C is always passed by value. So if I just say my function I, I'm not really passing I, I'm passing the number 10. This is exactly the same as if I had said my fun 10. So over here in my function, yeah, I can set I equal to 20 in here, but guess what? I is a local variable inside this function. This I has nothing to do with that I. The reason being that I'm not passing I, I'm passing the value of I. And if I said my fun 10, and in here I said I equals 20, there's no reason we'd believe that this is going to suddenly change to a 20. Alright, so if we want to be able to change the value of something in a function, here's what we do. Instead of passing I, we pass the location in memory where I is stored. And then in my function, instead of an integer, I say I'm getting a pointer to an integer, and let me call it something other than I. Let me just call it star pointer. And instead of saying I equals 20, I'm going to say take the thing that pointer is pointing to and set that equal to 20. And now we have a very different situation. What I'm passing is the address in memory where I is stored. And so PTR is a location in memory. Now if I set PTR equals 20, right, that has no effect on the address of I, right? I just passed a number which happened to be the location where I is stored. But this says, at that location in memory, I'd like you to store a 20. Well, what is at this location in memory is I. Why is that? Because what I passed is the address where I is stored in memory. So this takes a 20 and it drops it into memory at the exact spot where I is stored. So now when I come back here and I print I, I'm going to see a 20. Okay, that's the essence of pass by reference. We're passing a reference or an address of the variable I. And so we can use that to change the contents of I. And this is why we do ampersands when we call scanf, because we want scanf to change the value of the variables we pass to it. Alright, so that's star and ampersand and pass by value versus pass by reference. And C is always pass by value. In this case, the value we're passing is the address of location I. But that address is, in all practical senses, a reference to the variable I. So we can imagine that we're passing I by reference. All right, and then dot and arrow, right? So when you have structures, I think we might have mentioned this yesterday, but you know, if I have a struct node and it's got a data field and so on, and if I have a struct node n, I can say n dot data. That gives me this field named data inside this structure. But if I have a pointer to a structure and I want the data field of that structure, that's when I use this arrow notation. So it says take this, find the thing it points to, and then give me that thing dot data. All right, malloc free valgrind. So you know all about malloc statements. You've been using them for a number of weeks. It basically gives you access to a chunk of memory that will be reserved for your use. And so, for example, if I say integer star I, and I set I equal to 10, I'm probably going to segfault. Because when I say integer I, like this, the compiler says, hey, I need 4 bytes somewhere. And wherever those 4 bytes are, that's what I refers to. But when I say integer star I, it actually says, hey, I need 8 bytes somewhere to store a pointer. That's all that this does. And that pointer is called I. But does it point anywhere yet? No. It probably points to location 0. So if I start trying to store something at the location that I points to, I'm probably going to segfault. So we need to tell I where it should be pointing, and typically we do that with a malloc. And so we could malloc, you know, size of an integer. Or if we have another pointer we want to use, you could say I equals whatever that other pointer is. And this is when we do like temp equals root arrow right, right? We're copying pointers. But if you don't have a particular location in memory available to use, generally we call malloc to create a block of memory. And then after you've malloc something, eventually you want to free it. And if you don't free it, that's a memory leak. And valgrind helps you find memory leaks. All right, GDB, which hopefully you've been playing with. I've been seeing more and more students in office hours where we've been going through GDB. So, what do you want to know about GDB? Basically, when you compile, use a G switch, and it's perhaps less confusing if you just put that right after the GCC. But you can put this pretty much anywhere except after a -O. Remember, -O says instead of making a.out, call my output file this. And you can't put anything in between here. If I say -O-G, my output file will be called -G. Right? So put a -G somewhere. And you definitely want it to go when you're compiling your .c files. If you also put it on your links, it doesn't do any harm, but it doesn't seem to do anything. So yeah, remember to compile with -G, not link. And then once you're in GDB, what do you want to do? So you can set breakpoints. And you can break it either a function or a line number. You can say list to get a listing of your code if you're looking for a line number to break at. You can say start or run to begin execution, and you can put arguments on here if you wanted to run with command line arguments. And this will run until the code hits a breakpoint or an error or finishes normally. And if you've stopped, you can continue with continue, or you can single step with next or step. The main difference being if you're about to do a function call and you say next, it comes back after the function returns. If you're about to do a function call and you say step, it steps into the function, and now you can single step through that function. You can print an expression, so this could be a variable, it could be an arithmetic expression, it could be function calls, and so on. You can say examine to look at a memory location or a set of locations. You can set watch points, which say hit a breakpoint when this variable changes value. And let's see, am I missing anything? Print. That's probably the bulk of what you need. It lets you get into GDB, start your program execution, step through, stop when things happen that are interesting, look around and examine your environment. That's the bulk of it. I mean, there's a million more things you can do in GDB, but this gets you your basic functionality that you would normally, put in a million print statements into your code to try to find an error. This will let you step through and examine things as you move. BT is useful if you're doing recursion, but this is not an operating system course, so we didn't really start unwinding call frames and things like that. But if you want to, you can do backtrace and kind of see your history of calls and where you're nested with recursion. So that's basically GDB. And keep working with that. Now 223, we're working exclusively in Java, so we don't get to use GDB there. We may play with JDB, which is the Java debugger. But keep working with GDB. It will definitely save your skin in future classes, because you'll probably do a lot of C programming at a university, and being able to debug is going to be pretty critical. So that'll come back and help you out. Make files. So everyone's doing make files. and those look good. So, a way to capture recipes for building some target, and you say make, and the make command looks for a make file in your directory and runs from there. Um, let's see, 223, mostly command line Java or Eclipse or IntelliSense. Yeah, unfortunately, I think we're probably going to go with, well, we're going to start with command line, right? Our first few weeks of Java will all be command line, so Java C and Java to compile and execute. But when we start moving into GUI development, yeah, that's going to be Eclipse based. Um, and I've tried in the past to switch to things like IntelliJ. I've tried to go back to things like NetBeans, and Eclipse still seems to be a sweet spot for what we're trying to do. Um, IntelliJ to me is a little too in your face for really kind of learning Java. You type one character and you've got, 10,000 things underlined in red, and you've got all kinds of suggestions popping up, and it's like Clippy on steroids or something sometimes. That's just my experience with it. Um, it 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 forces you to spend time and energy learning IntelliJ instead of learning Java. So for a learning environment, I think we can do a better job with Eclipse, because on a good day, it mostly stays out of your way. Um, but I have to see what this looks like, because every time that I do this course, Eclipse has gone through revisions since the last time, and sometimes those are helpful, sometimes not. So I'll be pulling these out over break and seeing what makes the most sense for us. Um, and I don't want to just use command line, because when we start working with making windows and stuff, I don't want to get bogged down in, these are the 20 methods you have to use to create a J-frame. I like having some of that stuff set up for us with Window Builder. So we'll see. It's a bit of a balancing act, but right now the plan is probably we'll use Eclipse and Window Builder for making GUIs. And those GUIs tend to be platform independent. So, the stuff we write in there, if we write it in Linux, we can port it to Windows or OS X and it will run. Um, but depending on how much attention you pay to detail, right, you can find things like, this looked great when I built it under Linux and I got it to Windows, and my fonts are all squished together and my text gets cut off over here. Um, and truly writing something that's portable from platform to platform requires paying attention to a lot of these details, which we probably won't go into in 223, because we want to focus on, objects in Java rather than, particular widgets and such. But yeah, there's a good degree of portability, um, and if you're a little careful, it's pretty successful. All right, abstract data types. So basic idea of an ADT, right? This is sort of like a firewall. When you think about a linked list, what do you think about? You think about inserting, deleting, searching, traversing, right? Finding the maximum value, counting the number of things in the list. Those kinds of functions have nothing to do with how the list is implemented. It could be PA1, an array, it could be PA2, a bunch of nodes with pointers, right? But our main program shouldn't have to worry about, is there an array underneath here? Is there dynamic memory being allocated? And so on. So when we think of a linked list as, a collection of data that we can add, we can search, we can delete, right? That's the abstract view of a linked list. The implementation view of a linked list is, I have a array with these fields in it, and I have a magic value called myNull, and if this thing's equal to myNull, then that's the end of the list, right? That's not something your main program deals with. That's not what a linked list is. That's part of how this particular linked list was implemented, right? So it's the difference between the abstract concept of a grocery store and a particular Fred Meyer, right? So Fred Meyer has a parking lot that you get in here, and you go in this door, and the produce is on this side of the store, right? But the abstract notion of a grocery store is it's a place where one can go and buy you know, food and household items. All right, I don't know if that makes more sense. So recursion. So we've been doing lots of recursion, particularly the second half of the course. So recursion is basically where you have, say, an algorithm that involves using the algorithm itself. So it's solving a problem by breaking it into subproblems and solving those. And how do you solve those subproblems with the same thing that you're writing to solve the original problem? So examples of this, right? A lot of the stuff we've done with trees. What's the height of a tree? It's 1 plus the height of the tallest subtree. How do you tell if there's a number in your tree? Well, see if it's in the root or if it's in the left or right subtrees. Well, seeing if it's at the root is easy. Just compare it to the root. Is this thing in the left subtree? Well, you can just call your search function on the left subtree. And when we print the contents of a tree, right, if we do an in-order printing, what do? We say, well, let's print the left subtree, print the root, print the right subtree. Well, how do you print the left subtree? Call the same print function that you just wrote. Okay, so that's essential recursion. And the main thing to all of that is being able to think about recursive algorithms and then implement them in code. And you can find lots of things that can be implemented recursively or described recursively. For example, the nth factorial number is just n times the n minus first factorial number. And in edge case, if you call it with 1 or 0, you should just return a 1. So suppose you want to find a character inside a string. So find some string and some character. Well, this is easy to do recursively, right? If string is empty, then no, we didn't find the character in there. If the first character of the string matches the character we're searching for, then yes, we did find it. Otherwise, let's just search, starting with the second character in the string. Let's just search that for our character. And if it finds it, we'll say, yes, we found the character. If it doesn't, we'll say, no, we didn't. Right? So that's a recursive version of searching a string for a character. Check the first character. If it matches what you're looking for, you're good. If not, just check the remainder of the string and answer whatever that answered. So you can think about different algorithms with recursive versions of the algorithms, and then we can write code for those. All right, stacks and queues. So we played with these. You did some code with these. So main thing to remember, stacks are last in, first out. Queues are first in, first out. So stack, that's a LIFO. We have a notion of top of stack, which is the point where we're going to push things and we're going to pop things. And push and pop. This adds to the stack, this removes from the stack. And those happen at some point in the stack that we usually call the top of the stack. A queue is a FIFO. And so instead of a top of a stack, we have a head and a tail because we insert and remove from different points in this structure. So we have a head and a tail. And we could think of these as add and remove. And we always add or insert at the tail. And we remove from the head. So it's got 2 action points instead of just 1. And we can implement this with a linked list. You've done that in a programming assignment. We can also implement this with an array. And for an array, we basically have this notion of a stack pointer, which tells us where the top of the stack is. And so you want to push, you copy into where the stack pointer is, and then you increment your stack pointer. Or you can go the other direction, depending on which way you want to grow your stack. A queue you can implement with a linked list, and that's what you did in your PA, and you can insert at one end, remove at the other. But we could also implement this with an array. And so you have to know where you're going to insert and where you're going to remove. And when you want to add something to the queue, right, you basically use the tail to know where to store it, and then you move the tail and so on. And the one slightly funky thing about array implementation of a queue is the 2 ends are connected together. If we store something right here and then we increment the tail would normally fall outside our array. So at that point we just wrap it around and move the tail back to the beginning. And so if you think of your array as being a circle, where this is element 0, 1, 2, and this is element n, well, if you go beyond this, you go back to location 0. So that's the mention of a circular array here for implementing a queue. All right, hashes are basically associative arrays. And so the goal is, to be able to store data in an array. And if we have our data keyed by an integer, we can say, give me, data item 0, data item 1, data item 2. We can just make a plain old array. And the data item corresponds to, the index of the array. But if we want to store our data based on something like a name, or a string or something else, we can't use a string to index an array. So what we do is we make an array which is indexed by integers, but we have a hash function. And so our key goes into this hash function, and what comes out is an index, which tells us where we should store our key in our data. So this would be some key, some data value. Okay, that's the whole idea of an ideal hash. You take your key and you turn it into an index in this array, and you store your key and data at that index. And so if your key is a bunch of characters, maybe you add up the ASCII codes and reduce modulo some number to get this integer index. I am writing, thank you. So take your key, run it through a hash function, get an index out. That's where you store your key and your data. All right, so that's an idealized hash. But the problem is there may be more than one key that maps you to the same index. So that gives you a collision. And when you have a collision, there's 2 ways we talked about to manage that. The first is probing, and the idea of probing says, let's add a second input to this hash function, which we call a probe number. And the first time you hash your key, set this equal to 0. Get the index, store your key data value there. But if when you do that, you find there's already something in this location, well, hash it again, but with a probe of 1. And that'll give you some different index, and you store your key data pair there. And if that was a collision also, then hash again with another probe equal to 2 this time, and that'll give you some different location and so on. So that's an approach called called probing. A different approach to managing collisions is chaining, and for chaining, basically each of these points to a linked list. and any key data pair that maps to this location, that key data pair is going to get stored on this linked list. And it's kind of a compromise. If we just use a linked list for storing all of our data, that's terrible performance, right? That's order n performance for search and such. If we do this, this basically breaks our data up into a bunch of smaller lists. So if we have 1,000 things in our hash table and 1,000,000 pieces of data, well, our linked lists are probably about 1,000 long, which isn't too bad to search. A lot better than 1,000,000. Okay, so that approach is called chaining. So those are the two strategies we talked about for collision management. Probing, where we do multiple hash attempts, and chaining, where we do linked lists. And the note on deletion here is if you're doing probing and we delete, say this entry, well, if we search for something that originally collided with this and we see that there's nothing stored here, we need to know that there used to be something there, so that we know we should rehash with another probe and try to search for our data at another location. So when we draw this out on paper as an array, we also needed some other fields. One of them was valid to tell us whether there was something stored here. Another one was deleted to tell us whether there had been something stored there. So that's just implementation details for probing. All right, trees. This has been our main topic, right? So binary search trees, fundamental property. Everything to the left of the tree is left of a root is smaller. Everything to the right of the root is bigger. Depth is the number of hops from the root to a node. So if you have a root and a node, the depth of this node is 1 because it takes 1 hop from the root to get there. If you have just the root, the depth of the root is 0 because it doesn't take any hops to get from the root to the root. And then the height of the tree is the depth of the deepest node. But we usually deal with height recursively, because we can also say height is 1 plus the height of the tallest subtree. And balance we usually deal with recursively. Trees balanced if the subtrees have close heights to one another and the two subtrees are also balanced. And then traversal we mentioned a little while ago with recursion. Left node right is in order, node left right is pre-order, left right node is post-order. Those are depth first. They move down the tree before they start moving across. And those are generally stack-based, which is what recursion is. But we can also do breadth first, where we move across each level and slowly move down, and we can implement that using a queue. Searching, inserting, deleting, these are all recursive algorithms, right? And you've coded these up in PA4, and we've worked on them since then, and so on. So hopefully you're good on those. I will not ask you about AVL trees, even though we talked about them a little bit. We'll deal with them probably in 223. We might do some coding around those. Tries are these trees where we have really wide nodes. So instead of just a left and right pointer, we have, in this case, for storing a trie of words, 26 pointers, which point to potentially 26 children. And when we're searching for something, instead of just saying, is this bigger or less than the root, right? What we do is we look at the first letter of the thing we're searching for, and we look at that pointer. And if it's null, the word's not in our trie. But if it's not null, it will point to another node, and then in that node, we search for the pointer corresponding to the second letter of our word. And we keep doing this until we get to the end of the word, and then if this end of word string is set, we know the word is stored in our trie. AVL trees were these balanced trees that we talked about for a couple of days at the end of last week and start of this week, where we were doing these rotations, left, 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 right, and so on. And they won't be on the final, but we'll probably resurrect them in 223. The final will be probably about half coding and half conceptual, fill in the blank, matching, who knows, haikus. So tries, I'd like you to understand the basic concept. I'd like you to be able to maybe answer questions about this kind of structure, or maybe, draw some arrows to add something to your try, and so on, along the lines of the things we did in class. Dynamic programming, we did that in that was sort of the essence of everything we did last week. So, basic concept, we're caching results. So if you have an algorithm and you want to add dynamic programming, what do? You add one thing in the beginning, which says, see if I've got a cached result. And you add one thing at the end, which says, I'm about to return an answer, let's save that in our cache. And that speeds things up. All right, sorting. So you should be able to answer conceptual questions about this. You should be able to take a list of numbers and show me the first few steps of a sort. So these are the sample problems I posted a few weeks ago on Canvas. Or look at the first few steps of a sort and answer questions about it. What kind of a sort is this? And so on and so forth. Bubble, insertion, selection. These are our order n squared sorts. Insertion, we do the sorting when we put our numbers into the output. So we pull them from the input, just from top to bottom usually, but we put them in the right spot in the output. That's where the sorting happens. Selection, we choose from our input numbers so that we're choosing them in order, and we just put them into, one right after another in the output. So the difference here is where the sorting takes place, when you add to the output or when you select from the input. Merge sort is a log n operation, so an n log n sort, and the idea was you've got a list of numbers you want to sort, split it in half, sort each of those, and then interleave them so that they end up sorted. And how do you sort those two sublists? Use merge sort. Okay, so it's recursive. Quick sort was this idea of it was a sort involving pivots. So you have a bunch of numbers. You have a last number which we call the pivot, and basically we move from this end until we find some number that's bigger than the pivot. And then we move from this end until we find some number that's smaller than the pivot, and then we swap those. And then we continue until we find some number that's out of order and some number that's out of order, and we swap them. And when we're done with this, when our two arrows have met, we know that everything to the left is smaller than the pivot, everything to the right is bigger. So we just go ahead and we swap the pivot in at that collision point. And now everything over here is smaller than the pivot, everything here is bigger than the pivot. So sort this sublist and that sublist and you're done. And how do we sort the sublist? We use quick sort. So it's another recursive. Where's the document on Canvas? It might have been an announcement that was posted. In fact, there was definitely an announcement about it. And then heaps relate to heap sort. Oh, so know the basic performance issues of performance characteristics of this. So n squared, n log n, and so on. Cool, good. And then heaps, are this idea of a max heap or a min heap. So if we have a max heap, the main characteristic is each node is bigger than its children. And as long as each node is bigger than both of its children, it's a max heap. And since we have a max heap, the largest number is always at the root. And so if we want to remove the largest number, we just pull off the root. And then you take the last thing in the heap, move it up, and you down heap. So you move down and make sure the heap property is satisfied. And when you want to add to the heap, you put your new number in, whatever the next spot is to preserve that heap shape, and then you up heap. So move up, make sure the max heap property is satisfied. So there's questions about that on that Canvas document, and so know how to pull something off, add something in, right, and the upheaping and downheaping that go with those. We can also build a heap starting with a set of numbers by heapifying instead of just inserting. So that's a special operation and it's more efficient. And the last thing was implementing a heap with an array. And if we store these nodes in order in a plain old array, and we start with index 1 instead of 0, then simple arithmetic operations let us move to children or to parents and find the first and last thing in the heap. So that was just implementation details. So yeah, and this is all boilerplate from like midterm and such. So be able to write some code, write pieces of code, analyze code, modified code, and then conceptual questions, short answer, things like that. All right, we are out of time. Come into Zoom on Wednesday, 11 o'clock is when your exam is. It will be an item on Canvas that will unlock at 11 o'clock on Wednesday. I strongly recommend being in Zoom during the exam so I can mention corrections and clarifications. No office hours next week, but shoot me an email if something comes up. And yeah, just thanks again for the quarter. It's been a fun and interesting one for me. Good luck with your other tests. I will see you Wednesday for your final, and then I will see you in 223. So have a good one, and I'll see you in 215 in a half hour if you're there. All right, thank you.